A very good afternoon to all the participants who've joined this session today. I hope I am audible, visible, and you can see the PPT on the full screen mode. Please respond to the chat box so that we can get started. Thank you. Thank you, participants. All right, let's begin. Thank you so much. Let us begin with a few thoughts. I want you to ponder over these questions that you see there up on the slide. Do you like waiting in queues? Do you think queues can be avoided altogether? Do you really think it has any relevance for businesses? Can waiting lines be made better? The entire session is going to be outlined around discussing all of these points today. I'm sure the answer to the first one is an affirmative no. None of us like waiting in queues. So let me point out to the agenda of today's session. I'm going to be talking about the significance and classification of queue management systems, take you through a host of different applications of queue management systems, bring to you some perspectives alongside of stochastics involving queuing models. And towards the end, I will take you through a discussion on the empirical evidence, which relates to Monte Carlo simulation for queuing. So let's look at the various instances when queues are generated. Take a look. So you have queuing up of customers outside grocery outlets, at the checkout counters, a situation of the past, and today you can see people in rings of circles thanks to the pandemic situation. Cars waiting in the assembly lines, messages waiting to be transmitted through the routers, orders placed on e-commerce portals which are queued up. So in a nutshell, this means that when you're talking about entities which are queued, you have customers, that's human beings, you have objects, you also have entities such as orders which get queued up for service. Participants, I want you to take a look at these numbers. These numbers do speak. This was a study done by the Qminder, a queue management solution provider, and Adyen, a payment gateway platform, among UK shoppers and also Hong Kong shoppers, which reflects some intriguing statistics. You can see that not more than 73% of the customers are willing to wait for more than 5 minutes. 74% would probably shop in a competitor's store if they perceive the queue time to be quicker. On your screen to the right, you can see the revenue losses, £12 billion lost to competitors and also because customers leaving. What does this go to tell? It tells us three very important aspects. One, with respect to the customer expectations of waiting times. Second, talks about brand loyalty and the intentions to switch if you get quick service at some other place. And third, talks about how revenue losses can happen if queues are improperly managed. So what does this tell us? Queue management is imperative, all right? Dr. Richard Lawson, a professor at the MIT, popularly called Dr. Q, has done a lot of research in the area of queuing psychology for over 3 decades. He pointed out in his studies that every queue, while it poses a problem, if well managed, it is indeed a business opportunity. With respect to queuing and waiting times, there are two perspectives one needs to understand. One is the actual duration of the wait, while second, it is the perceived duration of the wait. This is where the perspective of queuing psychology really pitches in. Let me tell you an interesting story which is generally seen in queuing literature. In the United States. So in one of these complexes, the high-rise buildings, people always kept complaining, saying that the elevator took a long time and they had to wait and they had to continuously queue up there. So the team there tried to do a workaround. A month down, they came up with a solution which was very, very simple. They placed tall, long-standing mirrors adjacent to the elevator in every floor. And you know what happened? A month down, the complaints exponentially dropped, practically dropped to zero. So this reflects on how important the queuing psychology is. So in all, the waiting time was somewhere converted to the occupied time. So going further, again, highlighting the importance of how the experience really matters. I would like to take the example of Disney's queue management strategy. You know that in theme parks, you have a number of people crowding up there at the amusement parks. Probably not a situation now, but something that we're going to definitely see going further, and also a sight of the past. They follow 3 strategies to manage queues efficiently. One is queue chunking. Queue chunking is basically a modality where the entire physical design layout is such that when you're standing at a particular position, it looks as if you have very little number of people in front of you. So that's a physical way of disguising and building lines. The second is inflated waiting times at every attraction. So you tell the customer, probably project there in those digital signages that says, hey, it probably is going to take 30 minutes to take this ride, but in reality, it possibly takes just 20 minutes. So the customer feels like he or she is waited less. Third is an interactive queue modality, which is what you see there in the picture. So you engage customers and make them feel like they have waited less. Along this line, I would like to also quote what is called as the Parkinson's law, which was given by Cyril Northcote Parkinson, a British historian in The Economist, where he said, work expands was to fill the time available for its completion. So in the queuing context, it basically means this. If you're able to liberate resources, in the context of the queuing, when I'm talking about resource, I'm pointing to the waiting time. So if you're able to reduce the waiting time for the customer, let's say instead of 30 minutes, the customer shops there in 20 minutes, and I get that buffer of 10 minutes, this is going to get reinvested back. So I probably go around the store, do some window shopping, plan potential purchases, and it gets back into the original context. So in all these instances, I'm basically pointing out to the relevance of queuing psychology. Let's look at the queue management system market classification, which is along 2 lines. One, based on the end users. So you have a number of end users like hospitals, telecommunication companies, retail, banks, among many others. With respect to the type, there are 2 broad classifications, linear and virtual queues. So let's know more about them. So let me bring to light some of the leaning queuing variants. So when I'm talking about linear queues, these are nothing but physical queues that you generally see at fast food counters, in supermarkets, etc. There are different variants there. The most common one seen is a single counter environment. That's your single queue, single service point, the FIFO, the FCFS, which means customers are served in the order of their arrival. So this is very popularly seen and requires very minimal planning and also layout considerations. But of course, the concerns are very high in terms of bulking and reneging. Now, what do I mean by bulking and reneging? Bulking and reneging are basically impatient customers. While a customer is termed as bulking, if he or she looks at the system, finds a very long queue and gets demotivated, does not even enter the queue. When you're talking about a reneging customer, this individual sticks on to the queue for a while, but does not take service, but nevertheless exits the system. So this is higher because you just have a single queue. The second variant is the multiple queue, multiple service point. Now this is used in, this is a common sight in fast food counters where let's say you have 2 separate counters, one for the beverages and other for the food. In say supermarkets, if you segment customers based on the size of the basket, so shoppers with basket size of less than 10 items are in one queue, while more than that in another queue. So this enables segmentation of customers based on service needs and also caters to the heterogeneous service times. So when I say heterogeneous service times, it basically means that while a customer with who's shopped with 10 items definitely is going to take less time compared to somebody who has a cart full of items. But what is indeed the trouble in multiple queue, multiple service points? In many instances, you can see jockeying is a common phenomenon. So you can see customers moving in from one line to another, expecting to get quick service. So that's on the flip side. The third variant that I'm talking about is the single queue multiple service points, commonly called as the Serpentine Lines. So this modality, if integrated with an interactive customer experience, is a delight. Let me tell you why. Because in this case, there is no jockeying, so it definitely minimizes the customer anxiety. Everybody is held up in one single queue itself. But of course, it requires larger floor space. And if you have customers with more number of items, yes, it can affect delivery times. The advantage here, one that I'd like to quote, is with respect to shorter variances with respect to waiting time. Now, when I say shorter variances, I'm comparing with the other queuing configuration. So in a multiple queue and a multiple server mode, if you end up in shorter lines, you serve faster, while if you end up in longer lines, it gets even longer, your service time. So that is a variance element which I'm pointing out to. So this is effectively used. You can see an image there which reflects as an example there. Now let's talk about virtual queuing. So here, you're not confined to a physical waiting spot, that's waiting mobile. Now, in this context, I would like to give the example of SBI's No Queue app, which was launched in 2017 for select branches where the customer had to take, could maximum avail 5 services and had to take virtual e-tokens. So here what happens? It is definitely a time saver because you don't need to end up queuing at the branch for long. And this kind of a virtual queuing framework is generally integrated with the physical queuing or the linear queuing. What do I mean by that? Now you wait mobile, but when you enter the service destination, let's say you enter the bank, you either have a staff who enables entry into the system through a physical queue modality, or there is a self-serve kiosk where you need to register and then you go further. So that's how these queue management solution providers integrate the virtual as well as the linear queuing. I want you to observe 3 layouts or 3 variants when virtual gets integrated with the physical. So you do a registration in, say, the kiosk, and you enter the waiting area. Now, when you're looking at the waiting area, nobody needs to line up there because that's mobile waiting. You can just randomly be seated there. And as the server gets free, each person enters the service. While we look at the second and the third variants, I want you to observe something interesting called as the buffer zone. So this buffer zone is basically an area where the next customer who needs service is going to wait. So why is this second and the third variant much more useful than the first one? Because for the server, it is going to reduce the time between 2 services. So the inter-service time is reduced because there's always a time lag when you have a person waiting and then coming to the server. And obviously, it also translates into reduced waiting time for the customer because you already have one person lined up right there. So those are 2 variants that you see with the buffer zones, which is again an efficient design layout. So I want you to take a look at some of the companies in the queue management space: Qmatic, Qless, Qminder, Skiplino. There are many of them which develop solutions both in the modality of the virtual as well as the linear queuing framework. Let's just take a look at the trends. You can see how the QMS market is growing. And yes, indeed, thanks to the pandemic, with no overcrowding and social distancing norms, these companies are definitely there to stay and provide better solutions. So let me take you through an array of examples across implementation of QMS in different sectors. First, I would like to take the example of Rainbow Children's Hospital, which is a children's super specialty hospital. They have designed efficient patient appointment scheduling systems with follow-ups and timely notifications through an app mode. And I want you to observe that there is a very interactive digital signage constantly giving a lot of information there. And you can also see those interactive games there. This is a children's hospital. So somewhere, I want you to connect to the point that the queuing psychology really matters, where the perceived time can be made lesser by designing and implementing such kind of systems. Rema Children was also a pioneer in introducing something called as an alpha care, which is an innovative device which enables better inpatient management. So when I say inpatient, these are people who get admitted in a particular setting, and this has reduced nurses' turnaround time. Let me tell you how. When you generally look at inpatients, they constantly ring the bells, and the nurses will have to attend to that coming immediately. Now, in many instances, these queries or the bells are rung not just for clinical care, but for various other things like maybe queries related to billing and discharge, which really does not connect to what the nurses need to do. So in this case, what happens, there is somebody else also queuing up there, another inpatient who needs the nurse's care. So that person ends up waiting. So this particular design mode or the alpha care basically enabled that these queries get routed to the respective departments and more clinical hours of the nurses are available. So you can see that it definitely resulted in reduction of the turnaround time for addressing patient calls from the bedside. So that was a way of improving the inpatient experience and enabling better inpatient queuing management. I'd like to talk about another example. This was the AMSOPD transformation project in collaboration with the TCS implemented. Just take a look at the numbers. You can imagine the number of patients who drop into AIMS at the OPD, 10,000 patients per day, 55 departments, 2,500 capacity. I mean, that's huge, with a minimum waiting hours of 6 to 8. So I'm just presenting the highlights of the finding. So this appointment scheduling system and there was probably a makeover of the entire way in which the system was designed. Presenting to you the highlights, multiple registration counters were discontinued. So what happened, a patient who needed service maybe at with a general physician, a radiology department, etc., had to register at multiple counters. So that created a lot of congestion and increased a lot of time. Second, they also planned on increasing the seating capacity to manage congestion. And another very interesting observation is bringing in exit counters. Now, this is very important because when you're setting up an efficient queuing design layout, if you have the entry and the exit to be the same, you will see that it results in a lot of congestion. So they actually saw that there were about 18 OPD exit counters introduced. So the net result was a reduction of the waiting time to 2 hours. You can see that it was 4x more. So I think that indeed was an achievement. Something of a common sight when we all visit, let's say a Geo center or an Airtel outlet. You can see multiple people there waiting to serve you while a huge number of people crowded there asking for different things. Somebody wants a new SIM card, somebody's there with a customer grievance. So you have a lot of queries that people are somewhere creating a sense of chaos in that space. So Qmatic implemented this along with Fujitsu across 346 Vodafone stores in UK, where they introduced this kind of a self-serve kiosk, which was a touchscreen technology to match the queries of the customer with that of a service advisor. So this kind of a mapping was very useful because customers who required specific service were mapped. So this generally reduced queuing and very importantly, reduced the leave without being seen ratio. This LWBS ratio is a very important metric in designing queuing systems because that tells you how many customers are lost. So that's again a potential business opportunity. So this index is an important metric in that sense. Also talking about DigiAtra, which is a Government of India initiative, the pilot implementation, which was done in the Hyderabad and Bangalore airports in 2019, a facial recognition biometric enabled system, which ensured that identity check did not happen in multiple points. So that is flying like a breeze in an airport setting. So a lot of such implementations across the different service sectors indeed helps managing queuing systems a lot more better. Let me take a minute to play a video. This video is just going to be for 2 minutes. Then let's talk about Amazon Go, no lines and no checkout.
4 years ago, we started.
I hope you got a glimpse of where queue management is really trending. So while we're looking at optimizing waiting lines, this is a complete different scenario where you just have no waiting lines at all, cashless grocery stores, no checkouts. You just, so I think I would like to say this is shopping like a breeze. So that's where queue management systems are really trending. Moving on, let's look at some of the emerging queuing solutions which have come in as a result of the pandemic. They call it the pandemic impact. YQ is a chatbot. I'm just going to take a few examples. YQ is a chatbot used for grocery order placement from nearby local Kirana stores. This was implemented by a startup in Delhi, where it enabled people to ensure they could shop from the nearby grocery outlets and they could avoid queuing up. The second instance is the BevQ app. This was developed by a startup again for a Kochi-based startup for Kerala State Beverages Corporation. I'm sure we all know what happened during the extended period of lockdown when liquor sales started. So while we talk about liquor from the perspective of not being good for health, and it's also a social issue per se, you just had people flocking up outside the stores. So this ensured that only those people who register in the app could come in there at the counters. And it also reduced the frequency of the purchase. So people could not purchase for more than once in a span of 4 days. So this was implemented not just to probably bring down consumption, but also manage the kind of queues which can come in due to liquor sales, especially post the impact of the extended lockdown. The third example quoting is AI Cafe, a digital cafeteria management platform, which was developed for the IT park in Trivandrum. So you had a lot of IT offices which opened work, and people were definitely apprehensive of going down and even to the cafeterias to go and get food. So here they got food push notifications. Once the food was ready, they could just go and pick it up. So this was another very effective way of reducing crowding in the cafeteria locations of the IT firms. SafeQ by WaveTech is another automated occupancy control solution implemented in the healthcare, which is going to count the number of people. So there are counting sensors which ensure that only the required number of people are there within a framework or within the setting, because you know that a hospital is a place where people are susceptible to a lot of infections, and one must definitely look at avoiding overcrowding within a hospital setting. So this was a solution designed to enable that. So that's giving you a broad perspective on the significance of queuing models. We've looked at the different queuing variants, the linear, the virtual variants, and I've taken you through a number of applications to get a brief insight on where and how queue management systems are implemented. My second part of the discussion is going to revolve around queuing models. So I'm going to give you some insights revolving the kind of mathematical elements, stochastic elements, which are embedded when we are talking about queuing models, which is definitely at the background of all of that we have discussed. So indeed, there is a twofold objective to queuing models. One is to examine the existing system and quantify the operating characteristics. I'll tell you what it means as we go further, and how to make the system better. So let's take a look at some of the queue model variants. Now, any queuing system is represented by the 6 parameters that you see there. I'm going to elaborate on this A, B, C, D, E, F as we go further. That's going to be the scope for our discussion. So Dr. Kinder gave us this notation to describe and understand the different variants of the queuing models. A defines the arrival time distribution, which basically tells us the pattern of arrivals, which is indeed a probability distribution. B models the service times. C represents the number of servers in the system. D talks about the maximum number of customers in the system. So D is a parameter indicating the system capacity. E talks about the size of the source, which can be finite or infinite. I'll elaborate going further. And F talks about the service discipline. Okay, so one needs to realize this. So when you're talking about any mathematical model, you need certain inputs. And then you have the deliverables in the form of the outputs, which are nothing but the performance indicators. So in the context of a queuing model, the inputs are the arrival rates and the service rates. So if you're able to model this for a particular system, this indeed is the basis for developing and quantifying the various performance measures. At this juncture, I'd like to define what is a system and a queue. So one needs to have an understanding on the LS, LQ, WS, WQ, and the various metrics that I'm going to talk about. So when I'm talking about a system, it encompasses the queue plus the one at the service facility. So let's say I'm talking about a billing counter in a supermarket. You have 9 people who have lined up and one is there with the server. So it means that you have 10 people in the system while 9 queued up. So in this context, when I'm talking about LS and LQ, this represents the mean number of customers who are there in the system and the queue respectively. W is the parameter indicating the average waiting time in the system and queue. And rho is a very important metric called the service utilization index, which gives us an understanding of to what extent the server is busy. So when you actually evaluate 1 minus rho, it tells you the time that the server is free or idle, and the time can be suitably redeployed. So let's go further and let's look at understanding each one of these elements. I want to first talk about the arrival time distributions. Let me take an example. Let's look at a scenario. I want you to look at the image on the right. Scenario where, let's say there is a server failure in a particular office setting at different instances of time. So on day 55, you have a server lapse. On day 145, day 156, day 194, you can see those different discrete instances. I call them discrete because they are specific instances indicating the failure. So this is observed, let's say, for a period of about, say, 500 or 600 days. So on an average, you know that, or it can be estimated, just for an example, that the server fails or there is a lapse on an average of 60 days. So this average is determinable while you really don't know the exact timing of the event. I don't know if there is going to be a failure on day 53 or day 55 or day 56. The exact timing of the event is not known. That is why you call it as a random or a stochastic process. Same as the scenario when you're trying to model the arrivals into, say, a grocery store. So on an average, you will be able to predict based on the data, the number of arrivals into the supermarket. But at a particular instant, you are not able to say whether you will have one customer, two customers, three customers, how many are likely to walk in. This makes these stochastic processes. It can be seen that most of these random stochastic processes, discrete arrivals, can be modeled using a Poisson distribution. So the Poisson distribution is generally used to model such instances. Also scenarios like, let's say I want to model number of cars crossing a signal per minute, number of people who enter a grocery store per hour, number of orders which are placed in an e-commerce portal. So these are instances which can be monitored using, modeled using the Poisson distribution. So when these events are discrete, you will see that the time between two arrivals, which is what is called as the inter-arrival time, which can be modeled through an exponential distribution, which is Markovian in nature. Now, this Markovian property basically means it is a memoryless property. Now, what I mean by memoryless, this is an interesting property because it basically means that the past does not have an impact on how the future event is going to be. In the context of the example going back, where I spoke about the server lapse, let's say I have a failure or a server failure or a lapse in the system on day 55. You never know, you can have a back-to-back failure day 56, 57, or probably for a span of the next 100 days, you might not have a failure at all. So a past event or an occurrence of one event really does not have an impact on how the events are going to be in the future. So this is basically the Markovian property of the exponential distribution. So it can be seen that when you have arrivals, which can be modeled through Poisson distribution, the inter-arrival times will be modeled through the exponential. So these are commonly seen across random processes where lambda defines the arrival rate for the Poisson distribution. Now, a classic characteristic of Poisson distribution is that the mean and the variance and the parameter are actually equal to the arrival rate. So when I say arrival rate, it means the number of customers, say, who have walked in per unit time. All right. So that's talking about the arrival time distributions. Next, talking about the B element, which I showed you in the Kendall's notation. This is another very important input which needs to be understood while we are modeling. That's the service time probability distribution. Again, it can be seen that in most of the situations, in most of the random processes, exponential distribution is used to model service times, where the service rate is defined by the parameter mu, where 1 by mu nothing but represents the mean service time. So when you generally work with, say, real-time data, one way of checking whether my distribution is exponential is to look at the coefficient of variation, which is nothing but the ratio of the standard deviation to the mean expressed as a percentage. So for an exponential distribution, the mean and the standard deviation are the same. So if you see your data trending closer to a coefficient of variation to be 1, it means you're getting closer to the exponential distribution. So looking at the way the Kendall's notation is designed, so you have a number of classification of these queuing models. I just want you to take a quick look. I've just presented or just projected about 4 of them there. The M and M talks about the arrival time and the service times being modeled through an exponential distribution, which is what is largely seen. The G is a general distribution. So sometimes you will not be able to exactly model the distribution and know what is probably the shape, but then you will know the mean and the variance. That is defined through general distributions, where you'll see that the analytical solutions are a little more difficult and complex. Let me just show you a screenshot from Tora, which is one of the softwares which can model different OR tools. So the reason I put this across is to basically give you clarity on the aspect that if you have the inputs to the system, the queuing system in this case, which is nothing but the arrival and the service. So if I'm able to model these two metrics, you will be able to get the various performance indicators. So in a particular system, so you can just see an example where I've input lambda to be 10, that's your arrival rate, and service rate to be 12. In a one single server model, you can look at all these performance measures. You get your LS, WS, LQ, WQ, and all of these performance measures. Rho, again, is a measure of server utilization, as I told you earlier. So this means that 83% of the time the server is busy. So this is to basically bring clarity to the fact that when you have the inputs, which is nothing but the arrival and the service rates, if you're able to model them, you will be able to get a sense of these performance measures telling you how exactly your system behaves. Just looking at the transition diagram. So I want you to just take a look at the screen to the right. When you're looking at this, essentially this is nothing but any system which is defined. So in rings of circles, you see 0, 1, 2, 3, etc. It talks about how your system moves. So let's say you have one shopper who's entered the store. So your state from the time of observation moves from say 0 to 1, who enters with an arrival rate of lambda. From 1 to 2, your system goes when you have another additional shopper who comes in again with an arrival rate of lambda. So this is the way in which the system is generally modeled, and you build these transition diagrams indicating the state of the system at any given point in time. So typically, when you look at it from a mathematical perspective, we develop what are called as transition equations. Matrices are drawn, devised, and you evaluate the probability distribution, which is what is represented by PI. So PI talks about the probability of having I customers in the system. What's the probability of having 5 customers in the system at any point in time? And I don't want you to really look about the expressions of the formulae, but I want you to relate to the fact that this probability distribution depends on the input parameters, which is what is generally modeled. That's your arrival rate lambda and your service rate mu. So which is why I said when you have these two entities, your software will be able to give you the various performance measures, which is what we're generally looking at in order to understand how the system basically works. So moving on. So we've spoken about the arrival time distributions, got a glimpse into the service times, spoken about the multiple server context. Now I'm moving to the element of D, which is nothing but indicative of a system capacity. So if you look at the MMCN, what does this represent? This talks about a system which has Poisson and exponential arrivals with multiple servers, and you have a finite capacity. Now, how do I understand a finite and an infinite capacity? This basically means this. Now, when I'm looking at modeling a situation in a supermarket, all right, let's say at a given instance, 20 customers are allowed to shop, and the 21st customer needs to wait outside. I think this is the kind of a situation we're seeing in this pandemic, where the capacity of people within the framework of shopping is reduced. That is restricting capacity. So let's say in a healthcare or an OPD clinic, people consult or rather are allowed to consult on an appointment basis. So I have 10 people who have consulted and the 11th person is not allowed to come, which means there is a restriction on the capacity. On a particular day, there are only 10 people who are able to consult the doctor, let's say. So then you're talking about restricting the capacity, or we're talking about a finite capacity scenario. When this restriction doesn't happen, that is when you call it as an infinite capacity. So what changes? Now you see that with respect to modeling perspectives, there are transition diagrams, you have different kind of matrix equations developed and solved, but I'm talking about what changes in such a scenario. A new arrival gets blocked. So which means in the example that I took earlier, if the 11th person walks into the clinic, he or she does not get served. So in this context, there's something called as an Erlang's loss called formula, or the blocking probability gets evaluated. So this talks about the probability that the system is full or an arriving customer gets blocked. Does this have any relevance to a business? Yes, from two perspectives. One, if I'm able to evaluate this probability, I'm able to understand to what extent I can probably increase the capacity. That's one. Second, this is an important metric to measure because it talks about a lost business opportunity. So you know how many people have not been part of your system, who probably landed there, but because of a finite capacity scenario, the arrival gets blocked. So these are two perspectives that I wanted to bring to your notice. We'll next talk about the finite source variant. So now I'm moving to the E. So we've spoken about a finite capacity. Now I'm talking about a variant of the model, which is a finite source. Now this is interesting. So when you're talking about a finite source, let me take the example of a machine interference model. You can see on your screen an image on the right, which is probably something seen in a factory setting. So this can be seen in a manufacturing context, in textiles or in milling or grinding, where you have a set of machines there, automated machines performing specific tasks. And these machines are under the supervision of select number of operators. So if there is a machine failure per se, the operator needs to attend to it, probably restart and get it working. So in this context of queuing, we're talking about the repairmen or the operators who are the servers, while these machines to actually be the source, or in other words, they are the arrivals or they are the customers, if I have to put it that way. So let's say at a particular instant, there is a failure of more than one machine happening. You have maybe a situation of multiple machine failures. So, and an operator is assigned, let's say out of a set of 100 machines, 50 machines, he or she needs to attend to those various machines to find out what really is the issue. So then you will have the context of queuing. But this is an example in the context of a finite source, because at a point in time, you only have those 100 machines which can potentially fail in the factory setting. I don't have a new entry into the system which needs to be managed by the operator. So again, what changes? Your arrival rates or the arrival patterns are the ones which are going to change here. So when I have more number of these machines populating in the queue, which means, let's say I have an instance of more failures, obviously I have my arrival rate coming down because I have less in the source. So this is again an interesting optimization problem. Given failure and the repair rates, what should be the optimal number of operators or repairmen required to handle a group of machines? So yes, I've taken you through the A, B, C, D, E, and now I'm moving on to the last element, which is in the Kendall's notation, of course, which talks about the service of the queue discipline. So this talks about the order in which customers are going to get served. Now, while we have waiting lines, which can be of multiple modalities, single, multiple, etc. We've already spoken about the FIFO, the FCFS, you also have the last come, first serve. I just want to bring in some examples in the context of priority queuing. So in an emergency department, in a hospital setting, let's say somebody is getting treated with a normal illness. So let's say an accident case suddenly lands in. So what happens is the person requiring the service the most is going to actually be attended to. So these are models of preempting the service, which means you might sometimes stop serving the existing customer and move where the need actually arises. You're an Amazon Prime customer. So it means you get your orders probably in 24 hours, while probably a person not belonging to that category, it can take a couple of days. So that's priority queuing. You're a big basketeer. You have something called as a BB Star membership. You get those priority slots. So you are basically into a priority queuing mode where you get served quicker compared to another person. So that is from the perspective of the queue or the service discipline, or the order in which the customers get served. So I want you to really realize that when you're talking about queuing models, the model variants are huge depending upon the various types of probability distributions for arrival service times based on the number of servers you have, the system capacity, source capacity, and the various modalities and options of these queue disciplines. So that was a brief on the analytical models. Moving on to my last segment of discussion. Simulation in queuing is also very popular. Now, simulation is thought of to be as an alternative approach when certain analytical assumptions fail. Now, in analytical models, for example, when I'm talking about an MMC or an MM1 model, now I can use this model not just by assuming things, but I need to actually have my arrivals modeled through a Poisson distribution, and my service distribution should be, again, exponential. If that's not the case, I can't ideally adopt those models. So what happens when you're really not able to fit in a real life scenario these distribution patterns? Simulation is the answer. So simulation is basically this. You have data, say, for about 50 points or 50 observations. I create 500 or 5,000 odd trials and try and understand my system better by developing those performance measures. In this light, I'd like to talk about a small study that I had taken up in empirical evidence, which is basically modeling at a checkout point at a supermarket. I'll take about another 5 minutes to just take you through this brief session here. So you can look at the framework of the queuing process here. There were 2 servers and 2 queues. So you had the arrival of customers at the checkout counter, queuing up in 2 different queues. So at the service facility, you had 2 servers, and then of course the exit. I'm going to briefly describe how Monte Carlo simulation works. So real-time data was collected by an observation technique. And typically, when you adopt Monte Carlo simulation, you're going to use a process iterative approach, which means on a real time, you're going to observe and record how the system works, starting at some specific point. So let's say I start observing the billing counter at 4 p.m. and I go on to record data for 2 hours. So I'm going to record the arrival time, service time, waiting time in each one of the queues, reminding you there were 2 queues here. How many customers are waiting in the queue in the system at a given point in time. So this is a discrete simulation system because you are observing the system at discrete points in time. The basis of Monte Carlo simulation is it is going to use the concept of random number mapping, or it generates random events. Now, a lot of softwares can do it. Excel's rand function itself is used to generate random numbers. So I'm just going to take you through how this works. So for every server, so there were 2 servers there. The arrival time, service time, and waiting time distributions are generated. So just to take you through these various columns here, this is just an example for the arrival time. Similarly, it needs to be done for the service and the waiting time distributions as well. In the first column, you have the inter-arrival time. So inter-arrival time basically talks about the time between 2 arrivals and the frequencies here. So how many people arrived within what range of inter-arrival times. So this is process data for you for a total of about 21 customers. That is what is shown here. So you accumulate the frequencies and use the concept of uniform distribution to generate probabilities based on the relative frequency concept. So 2 upon 21, 3 upon 21. So you have these probabilities adding up to 1. Cumulative probabilities are evaluated so that you can generate what is called as a random number interval. So let me just take a few split seconds to tell you how the random number interval is generated. So I have 10% cumulative probability accommodated in the first row. So I have random number interval between 0 to 9. So accommodating for 10% range of values. So that way I continue and I go on. So you start from 0, 0 or 000. That's really a choice which can be made. So once this is done, this is when you start simulating. So if you observe for 21 observations versus data, and the remaining trials are all simulated. I've just put up a screenshot there reflecting for a few trials. So from trial 22 onwards, all right, so this is what is generated, let's say, by the Excel's rand function. So random numbers 59, 58, they're just generated on a random basis. Now, when a random number of 59 is generated, I go back to the random number interval. It falls in this class, corresponding inter-arrival time being 7. So that is the simulated arrival for a 20-second customer. So this customer is not part of my data, but I'm simulating it and creating it so that I can make better sense of the system. So this is done across for the arrivals, for the service times, as well as for the waiting times. And thereafter, performance measures can be computed. Take a look at some of the numbers there. So you can compute arrival times, arrival rates and service rates, obviously from the simulated data. And we can find all our performance measures. Most importantly, there are 3 things that we want to know. The average number of customers in the system at a given point in time, and also the queue. The waiting time, obviously, in the queue and the system. And very importantly, the server's utilization index. So you want to know to what extent the servers are busy or utilized. So on an average, you can see that for both of them put together, the server's busy, say, to an extent of about 77, 78%. So when you're able to get these estimates, it tells you how you can probably suitably redeploy your resources to do some other task. And it also gives you a sense of how much it takes on an average for the customer to wait. So you are able to understand these various system performance measures so that you can deliver better. So here are my concluding thoughts. There is really a no one size fits all approach when it comes to designing a queuing system. You have different kinds of service disciplines, different ways of handling arrivals, different queuing configurations along the lines of linear, virtual, serpentine lines, multiple servers. Now, depending upon the environment, the sector, what is really suitable needs to be decided. That's a very important point that I want to convey. Second, queue management systems basically have these larger goals. One, to reduce uncertainty by providing the customer some estimates of the waiting times. Second, try and provide a seamless experience. And very importantly, I'd like to reiterate on the point of appealing to the queuing psychology, which means make the customer feel like he or she's waited less. So you cash in on that time by creating an engaging experience, convert the waiting time to an occupied time by providing that interactive engaging experience. And more importantly, queue management systems are very important to improve operational efficiency. Thank you all. That was it from my end. It's time for discussion. I'm open for questions. We can unmute, I think.
Hello.
Yes, good.
Hey, good afternoon, teacher. How are you? How are you, ma'am?
Good afternoon, good please. Pleasure to hear.
Even though it was really too good after hearing you after so long. Ma'am, I wanted to ask, like, could you repeat? I was actually, I joined your session late because I was in the school, so I came late. But how far I listened, I wanted to ask one point. How can merchandising help in the queue management?
Now, when I'm talking about, okay, so just to answer that, how you probably place items on the shelves, I spoke about that with respect to the queuing psychology. So while you have customers waiting in the lines, they are obviously bored with nothing else to do. So can you create an engaging experience for them? Can you probably offer them something in terms of displaying something there? They could probably be the elements of window shopping. Normally, you see that when you go to any kind of a supermarket, you see those quick picks which are just kept near the billing counters. You have those, maybe those candies or chocolates, which you're just going to pick up. So I think those kind of interesting products should be kept right there at the shelves so that it is going to help in terms of also boosting sales.
Ma'am, one more question. As we have started in the form of education, we have started virtual learning. So what do you mean by virtual queuing? What is virtual queue management? I came across this word.
Yeah. So virtual queuing is basically a modality. Now, when I'm talking about linear queuing, it is customers physically queuing up at one place. So when you're talking about virtual queuing, you are waiting mobile. So I give you an example there with respect to various apps, and I give you specifically an example of the SBI's No Queue app. So you kind of take a spot there, and you are able to maybe take virtual e-tokens for different services. And you don't need to physically wait there. So you get these push notifications when you're registered on those queue management apps. You get these notifications which tells you on an average how long you will have to wait and how many people are there ahead of you. So when you get this kind of an estimate, you don't need to actually wait there at the system. You can probably finish off some work and get back there. So somewhere these virtual queuings must be integrated with the physical queuing through registration at a self-kiosk mode. So in that context, it's a mobile waiting. I hope I've answered your question, Gurpreet.
Yes, yes. Thank you, ma'am.
Thank you.
What difficulties?
Any more questions? Yeah, okay, from Ms. Ambika, yes, definitely the PPT will definitely be shared by our MDB team. Mr. Praveen, I can see a very long question there. Can we probably hear the question out? I would definitely like to respond to that. Can we unmute Mr. Praveen there? Okay, just to answer this question with respect to the time of arrivals. Now, I'm actually answering and responding to Mr. Praveen's question. So if you're looking at, you cannot really generalize. Now, in the context of the Monte Carlo simulation that I showed you in terms of what I presented, now, the supermarket was modeled, or rather the system was modeled at a particular time, say between 4 to 6 p.m. on a weekday. Now, if I'm going to probably model on the weekends, let's say, or maybe in a morning time or late evening, the arrival patterns, the service time patterns are definitely going to differ. So my answer to your question is this: lambda mu, that's your arrival rate and service rates, will definitely vary depending upon the time of the day and also the environment. Now, if I'm talking about, let's say, emergency department modeling, in the time of pandemic or maybe a flu season, let's say, these places are going to be definitely crowded as compared to a summer season. So these are time-dependent arrivals. I hope I've answered your question, Mr. Praveen. Okay, queue management in warehouses by Sandeep. Yeah, definitely you have concept of, I think, a service discipline which is employed there is a last come first served. So the items which are probably stocked up last there are the ones to get first served. And I think queue management is definitely important when you're talking about improving the operational efficiency. Effective from Ms. Ambika again. Queue management effective in hospitals and airports. I think I did give an example of the DigiAtra there in terms of how you can basically avoid these identity checks at multiple points. So I think that is crucial so that you can ensure that there is a kind of a streamlined checking happening only at one single point and people don't need to keep queuing up at different locations. In hospitals, yes, That's an area which I'm actually also trying to do some research on. In OPD, in the emergency department, also the inpatient unit. I think I spoke about an example of how Alpha Care in Rainbow Children Hospitals is actually useful in implementing and providing better experience in the context of inpatient management. So that's my answer to the query. I hope I've answered most of the queries that I've seen on the chat box. Falgun Madhusudan. Okay, is there a minimum number of data points you need to simulate using Monte Carlo to be able to come up with a reasonable estimate? Okay, Falgun, my answer to you is this, based on the knowledge and understanding that I have. Now, when you're observing, so if you're looking at minimum number of points to simulate, so I think one needs to realize that simulation actually does not give you an optimal solution. So you try and generate as many trials as possible so that when you're looking at finally getting down to your arrival and service rates, it has some kind of a conversion point, which means, let's say you do for a set of 100 trials, you evaluate your arrival and service rates, do it for a group of maybe another 200 trials, again, evaluate your arrival service rate. So it is something like an iterative process, and somewhere you need to see it converging. So that is the basis in which Monte Carlo simulation works. It is about generating a large number of trials so that you can converge, have the convergence of your input parameters to a particular point. That's my understanding and answer to your question. Okay, with respect to the ethical sector, Ms. Achinta Kumar, okay, so I think that just to quote one example in my knowledge, the DigiAtra, which I quoted about, there were a lot of tweets and also discussions on that, asking, is a facial biometric system, what kind of, is there really a sense of data privacy? Is it going to be misused? But I did also have an understanding that it is GDPR compliant, that's a general data protocol regulation compliant. And also that these kind of facial biometric systems, what I heard, once the person offboards the flight, it is erased from the system. So the facial kind of biometric details really are not stored in the context of DigiAtra. That's what I read. That's my understanding with respect to the ethical perspective. Okay, from Guru Dutt, explain about Erlang queuing model. Okay, Erlang is basically a probability distribution. Now, Erlang is a sum of, when I say a K-Erlang model, it is basically a sum of K exponential distribution. So it is a larger class of an exponential distribution. So in other words, you can say that an exponential distribution is a smaller version or a particular case of your Erlang model, again has a Markovian property. So in these kind of solutions, there are definitely analytical models, and when you're going to solve these matrices, you will get those performance measures. But today, rather than looking at that, we try and understand what the modeling parameters are, and we have a number of softwares which is going to help us get these performance measures with ease. So one really need not understand the nuances of the analytical models, but the background of working is something which we really need to have an understanding of. Whether it'll be applicable practically, yes. So an Erlang is, as I said, is a larger version of an exponential distribution and is nothing but Markovian again. Exponential is Markovian, so is Erlang. So definitely has a practical implication. I think with respect to the feedback links, the MDP team will definitely be sending it across. So yes, I think my email ID is also visible on the screen. I would definitely like to take a lot more questions offline. So please do interact. And if you have anything else to ask, you can definitely email and get in touch with me. Thank you all. It was a wonderful session. Thank you.